Have you ever wondered what's really going on inside a car engine, or a giant wind turbine, or even something as simple as a hand drill? Well, beneath the surface, there's this invisible world of physics and engineering. It's a fundamental set of rules that honestly prevent these powerful machines from just tearing themselves apart. Today, we're going to pull back that curtain and take a look at this hidden world. I mean, just look at this. It's this beautiful, complex dance of pistons, rods, and a crankshaft. You've got these immense forces being generated and transferred every single second. But how does it all stay together? What prevents this controlled explosion from becoming, well, just an explosion? That right there is the very first problem every single engineer has to solve. And that leads us straight to our first big principle: stability. Look, before a machine can do any useful work at all, it first has to be able to just hold itself together under some pretty incredible stress. So here's the core question, right? How in the world do you design a bridge or a building or a machine part so that all the pushing, pulling, and twisting forces just cancel each other out? Perfectly. The answer is one of the most foundational concepts in all of engineering. It's called static equilibrium. The easiest way to think about it is like a perfectly balanced game of tug-of-war. If both teams pull with the exact same force, that rope isn't going anywhere, right? In engineering, it just means that every single push is met with an equal and opposite push, and every twist is met with an equal and opposite twist. The object is perfectly still, perfectly stable. Now, this whole idea is captured with some elegant simplicity in these two golden rules. What that first equation is really saying is that for something to be stable, all the forces, the pushing and pulling from every direction, they have to add up to zero. And that second one, it's saying the same thing for all the twisting forces or torques. They have to cancel each other out too. It's just a state of perfect balance. And to make sure these rules are being followed, engineers use a really neat process like this. Say you've got a part that's being pushed or pulled in 3 different directions. First, you identify all those forces. Then, you figure out the single point where the lines of those forces would all cross. And if the forces are truly in balance, you can actually draw them as the 3 sides of a closed triangle. If that triangle doesn't close, the part is not in equilibrium, and you've got a big problem. It's this simple geometry that literally guarantees a machine's stability. Okay, so our machine is stable. Awesome. It's not going to collapse. But now we're facing a whole new problem. The power source itself is often really rough and uneven. Let's see how engineers get around that one. Think about a single-cylinder engine, like in a lawnmower or something. It gets one big, powerful push. That's the power stroke. But then it has 3 other strokes where basically no energy is being produced. This creates a really jerky, inconsistent delivery of power. So how do you smooth that out for a nice, steady ride? Well, you use a flywheel. A flywheel is basically an energy piggy bank. That's the best way to put it. It's a big, heavy wheel that takes all the extra energy from that one powerful burst and stores it up as rotational momentum. Then, during those coasting strokes, it releases that stored energy back into the system, keeping everything spinning nice and smooth. And you can see here just how this massive, heavy wheel does its job. It doesn't create any new energy, but what it does is it smooths out the peaks and valleys of the energy supply. Now, it doesn't keep the speed perfectly constant, but it dramatically reduces how much it fluctuates. And that is exactly what you need for a smooth, efficient machine. All right, so our machine is stable and our power is smooth. The next challenge is, how do we get that power from the engine to the wheels or to the blades or wherever it actually needs to do its work? How do you transmit all this energy without it slipping while maintaining a perfectly constant ratio and maybe even changing the speed or the torque as you go? The solution to this is one of the most brilliant and, frankly, ancient inventions in all of engineering. The answer, of course, is gears. Unlike a belt, which can slip, gears give you a positive, non-slip drive. Their meshing teeth absolutely guarantee a constant speed ratio, which makes them incredibly efficient and so versatile. It's why you find them in pretty much everything mechanical, from massive industrial machines to the tiny precise mechanisms inside a camera lens. But, not all gears are created equal. The very specific shape of the tooth, what's called its profile, involves some really critical engineering trade-offs. The common involute profile, for example, is way simpler to make, and it's more forgiving of tiny errors. But the cycloidal profile, while it's harder to manufacture, gives you a much stronger tooth with less wear. It just goes to show you that the final choice always comes down to the specific needs of that machine. Now here's a concept that sounds like a flaw, but it's actually a critical design feature. It's called backlash. That tiny little bit of wiggle room between gear teeth, that's on purpose. It's there to prevent jamming, to create space for lubricating oil to get in, and to allow for the metal to expand when it gets hot. It's a necessary imperfection that makes the whole system work perfectly. So let's recap. Our machine is stable, the power is smooth, and it's being transmitted perfectly. But we have one final invisible enemy to deal with, an unavoidable consequence of motion itself. Every single moving part, every spinning shaft, every tiny ounce of imbalance creates vibration. And if you just let it go, this constant shaking can lead to noise, excessive wear, and sometimes even catastrophic failure. So, how do you tame this unseen force? Well, first, you have to understand it. Vibration is just the oscillation or the to and fro motion of something around its resting point. But these tiny oscillations introduce stresses over and over and over again, and that can cause metal to fatigue and break over time, even at stress levels that are way below what it would take to break it in a single pull. And to see just how complicated this problem gets, just look at these diagrams. A really simple system with one mass on a spring has 1 degree of freedom. It can only move up and down. That's pretty easy to analyze. But as soon as you start adding more components, the number of ways the system can vibrate just increases exponentially. The analysis gets incredibly complex, really fast. And that leads to the most dangerous phenomenon of all, resonance. Every single object has a natural frequency that it likes to vibrate at. If some outside force, like the pulsing of an engine, happens to match that natural frequency, the vibrations can just amplify uncontrollably until the whole thing is shaking itself apart. This, by the way, is why soldiers are told to break step when they march across a bridge. So after tackling all of these individual challenges, stability, power, transmission, vibration, we can finally see how they all come together to create a machine that's not just functional, but reliable. It's really never just one thing, is it? It's more like a chain of solutions. Static equilibrium gives you the stable foundation. The flywheel smooths out the raw energy. The gears transmit that energy exactly where it needs to go. And finally, vibration analysis tames the destructive shaking. Each principle builds on the last, creating this single, elegant system. So the next time you turn a key and feel the smooth hum of an engine, or you see some massive machine operating flawlessly, just listen a little closer. You might just be able to hear that hidden symphony of engineering, a perfect balance of forces, all working together to keep our world in motion. Makes you wonder, what other invisible systems are hiding all around us in plain sight?